calibrated airspeed at flight level 270 when it experiences a reduction in outside air temperature. Okay, so how will Mach meter indication respond? That means what will happen to Mach number? Will that Mach number increase? Will that Mach number decrease, or will it remain constant? When your aircraft flies from a warm air mass into a cold air mass, right? So let's draw that. Let's say this is one particular air mass you are flying. This is your initial air mass, which is warmer than ISA, and then you travel to a new air mass which is colder than ISA, which is colder than ISA. Correct? You are flying at flight level 270. You are flying flight level 270. Correct? A constant flight level of 270, that is 27,000 feet, and at constant calibrated airspeed. At constant calibrated airspeed, let's say 200 knots. Calibrated airspeed 200 knots. This is a warm air mass. Let's say it is 30 degrees Celsius. You enter a cold air mass. Reduction in temperature will happen. So you enter 20 degree Celsius. Now, let's calculate true airspeed. Now, the true airspeed in warm air mass, true airspeed in cold air mass. Okay. So let's use CX3. Okay. So pressure altitude 27,000 feet. Calibrated airspeed we have considered 200 knots. Outside air temperature 30 degrees Celsius. So check the values. Pressure altitude 27,000, flight level 270, CAS 200 knots, outside temperature 30 Celsius, true airspeed 344.7, approximately 345 knots. Now over here, with a temperature of 20, with a temperature of 20, the things remain the same. Your TAS is 338.9 or 339 knots. 339 knots. So what has happened to your true airspeed? When you enter a cold air mass, it decreases. 345 has become 339. Now let's calculate the Mach number. The Mach number here will be TAS divided by local speed of sound. So TAS is 345. Okay. Now local speed of sound. Local speed of sound is 39.17 square root of temperature in Kelvin. So 30 degrees Celsius is how many Kelvin? 273 plus 30, that is 303. So 39.17 square root of 303 Kelvin. 39.17 into square root of 303 Kelvin, which is 681.8, or local speed of sound 682 knots. So what you are going to do to calculate Mach number, TAS divided by local speed of sound, 345 divided by 682. 345 divided by 682, that is 0.5. 0.5. Now let's calculate Mach number here. TAS, again same formula, TAS divided by local speed of sound. So 339 divided by local speed of sound. Local speed of sound will be 39.17 square root of temperature in Kelvin again. 20 plus 273, 293. So 39 square root of 293 into 39.17, which is 670 knots. 670 knots. So 339 divided by 670 is again 0.5. So what has happened to Mach number? Warm air mass 0.5, cold air mass again 0.5. So that means when you travel at constant calibrated airspeed, constant altitude, and you change air masses, you travel from warm air mass to cold air mass, or whatever, cold to warm, Mach number doesn't change. Mach number remains the same, 0.5, 0.5. So the correct answer here will be, how will Mach meter indication respond? It will show no change. Okay, it will show a constant value, no change. 62. How will Mach meter respond in a constant calibrated airspeed climb if the static source becomes blocked? If the static source becomes blocked. Now I will explain this question in two parts. How will Mach meter respond? Okay, when you are climbing in a constant calibrated airspeed climb, when everything is working fine, there is no blockage of static port. And in the second situation, I will take an example when the static source is blocked. So I will show you both cases, how will Mach meter respond. Now let's consider the situation when everything is working fine, static ports are not blocked, static pressure is getting registered perfectly. Now your Mach meter or your Mach number is nothing but a ratio between dynamic pressure, and static pressure. Dynamic pressure and static pressure, right? Now, when you're climbing at constant calibrated airspeed, say this is that air mass, you're climbing at constant calibrated airspeed. What happens when you do that? Atmospheric pressure, atmospheric pressure decreases. When you climb at constant calibrated airspeed, what happens when you climb to higher and higher altitudes? Atmospheric pressure, static pressure goes on decreasing, right? So, ideally, what should happen? Your airspeed indicator is nothing but a pressure instrument, correct? It's a pressure instrument. And this pressure instrument uses dynamic pressure to register the forward speed of aircraft or to represent or indicate the forward speed of aircraft in terms of knots. Dynamic pressure is nothing but created how? How is it created? By the speed, forward speed of your aircraft. Right? So that is your dynamic pressure, forward speed of aircraft. So when you climb to higher altitudes, when you climb to higher altitudes, atmospheric pressure decreases. This decrease in atmospheric pressure is nothing but what will happen? Registration, registration of lower and lower dynamic pressure, correct? Lower and lower dynamic pressure. So that means if lower and lower dynamic pressure is getting registered, is getting uh, transmitted to the airspeed indicator. So the indication shown by the airspeed indicator, that is indicated airspeed or calibrated airspeed value, that values will also go on decreasing, will also go on decreasing as you climb higher levels or higher altitudes. Remember this. Now, this is what will happen if you do to your calibrated airspeed. That way, it will go on decreasing. The values will go on decreasing. Now, if you want to prevent that from happening, if you want a constant calibrated airspeed climb, if you want your airspeed indicator to show a constant calibrated airspeed during your climb, you will have to. So I'm writing it here for a constant calibrated airspeed climb. What is necessary? You will have to climb at, at faster, higher true airspeed. Now, like I said, when you climb to higher altitudes, dynamic pressure or atmospheric pressure decreases, right? So you will have to, that means indirectly dynamic pressure that is getting registered, or the dynamic pressure, impact pressure near the pitot tube will also reduce or will also decrease in value. So in order to compensate for that, in order to compensate for decrease in dynamic pressure, you will have to increase the forward speed of your aircraft even more in order to generate additional dynamic pressure, which will compensate or counterbalance the decrease in atmospheric pressure surrounding your aircraft at higher altitudes. So that's why for a constant calibrated airspeed climb, it is necessary that you increase the forward speed of your aircraft or the true airspeed of your aircraft. So next step, when when true airspeed when true airspeed increases, Mach number. What is Mach number? Nothing but TAS divided by local speed of sound. So if TAS increases, Mach number will also increase. So TAS increases, so Mach number will also increase. Correct? Another formula for Mach number is dynamic pressure divided by static pressure. So like I said, if you want a constant CAS climb, calibrated airspeed climb, you will have to increase your TAS. You will have to increase your TAS. TAS increase is nothing but dynamic pressure. Impact pressure increase, correct? TAS increases means dynamic pressure increases. So over here, look, dynamic pressure divided by static pressure. So dynamic pressure will increase. Static pressure is nothing but the surrounding atmospheric pressure, that too you cannot increase or decrease. That is natural. So that will remain constant, or as you climb to higher altitudes, it will go on decreasing. So what will be the overall effect on this Mach number? Dynamic pressure is increasing. Mach number will also increase. Mach number is inversely proportional to static pressure. Static pressure decreases, Mach number will increase. So the overall effect is Mach number increases. So you can take this formula and understand it, or you can also use this Mach number TAS divided by sound formula and understand that. Now this is part 1. This is what should happen. Your Mach number should increase, that is option A, in a constant calibrated airspeed climb. Now look at the second part. If the static source becomes blocked, static source becomes blocked means what will happen? The work of static source or static port is to transmit static pressure to the airspeed indicator, right? Now if the static source becomes blocked, there will be no input of static pressure. No input of static pressure, that means your Mach number will only be uh, dependent on dynamic pressure and the static pressure which is in the ASI instrument previously. So let's say, I will take an example. You are climbing from 5,000 feet, 10,000 feet, 5,000 feet, 10,000 feet. Now the static pressure at 5,000 feet is, let's say, 200. It's not 200, but 700 millibar, let's say. At 10,000 feet, it is 500 millibars. Just for example, I know it's not 500, it's more than that. So 500 millibars. So what will happen? Static pressure will decrease as you go from 5,000 feet to 10,000 feet. Now your static port gets blocked, at 5,000 feet. Okay, the static port gets blocked at 5,000 feet. Correct? So your dynamic pressure, this is your ASI instrument, it shows dynamic pressure. Now dynamic pressure is nothing but dynamic pressure dynamic pressure is nothing but total pressure minus static pressure, right? So I will draw this diagram again at 5000 feet, at 5000 feet, at 10,000 feet. 5000 feet, static pressure is 700 millibar. At 10,000 feet, the static pressure is, let's say, 500 millibar. Your pitot, correction, your static port gets blocked at 5000 feet. So now, so at dynamic pressure is constant. Dynamic pressure, that is the forward speed of your aircraft, is constant at 5000 feet and 10,000 feet. So 5000 feet, your dynamic pressure is, let's say, uh, constant, and at 10,000 feet again dynamic pressure is constant. At 5000 feet dynamic pressure is total pressure minus static, so static pressure is 700 millibar. Dynamic pressure is, let's say, total pressure is, let's say, 1000. So dynamic pressure will be 300 millibar at 5000 feet. Okay, 300 millibar. Next, at 10,000 feet, your total pressure is, static pressure is again, static pressure should be 500 millibar, right? But since your static port is blocked at 5000 feet, outside or new static pressure outside your aircraft cannot enter inside the airspeed indicator. So whatever static pressure was previously at 5000 feet at the time of at the time of blockage, that will remain trapped in the instrument, and your instrument will make all the calculations only with respect to that, calculation, right? So at 10,000 feet, your dynamic pressure should be how much? Total pressure is, let's say, 1000. Static pressure at 10,000 is 500. So it becomes 1000 minus 500, 500 millibar. That means the dynamic pressure, the forward speed of your aircraft will increase. Okay, forward speed of your aircraft will increase. From 300 it has become 500. But since your static port is blocked, you are not going to subtract 500 from 1000. What you are going to subtract is, you are going to subtract 700 instead of 500. Okay, uh, you will subtract 700 from 500, and when you do that, you will get a dynamic pressure same as 300, or uh, something less than 300. So let's consider 300 only. So the 300, 310, 320, or 290, whatever. So the real understanding here is that as you go to higher altitudes, your dynamic pressure should increase. Okay, correct? Because it's a constant calibrated airspeed climb. So you're going to increase the true airspeed of your aircraft to get a constant calibrated airspeed climb. But here what you're observing is that due to blockage of your pitot, of your correction of your static port, the static pressure trapped inside, which is much more than the static pressure at 10,000 feet, trapped inside is 700. Actual is 500. So that's why when you do the subtraction, you will get the same lower value instead of getting higher values, 500, 600, 700. Correction. So that is the drawback. So what will happen to Mach number? Now nothing but Mach number is nothing but dynamic pressure divided by static pressure, right? So what you are observing, dynamic pressure instead of increasing is decreasing, and static pressure, which should decrease, 700 should become 500. But what we are observing, the decrease is not it's not happening, right? Because the static port is blocked. So ASI instrument is not getting or registering a decrease in static pressure in it. So what is happening to static pressure? It is increasing. Whatever static pressure was at the time of 5000 feet, the comparatively more static pressure, that static pressure will remain sharp in the instrument. So what will be the overall effect on Mach number? Dynamic pressure decreases, Mach number will decrease, inversely proportional to static pressure. So static pressure increases, Mach number decreases. So the final answer to your question 62 is, how will Mach meter respond in a constant calibrated airspeed climb? So part 1, I explained it should increase. But if static port is blocked, there will be an adverse impact. So Mach number will decrease. Okay. Understand the theory. Next, how will the Mach meter respond in a constant true airspeed climb if the static source becomes blocked? Again, this question has two parts. We will check the part number 1, in which everything is working fine. There are no blockages in the ports, static ports, pitot tube. So if you are climbing at constant true airspeed, let's say this is your air mass. Climbing in this particular air mass from 5000 feet, 5000 feet to a higher altitude of, let's say, 10,000 feet. Now what happens when you climb to higher and higher altitudes? Atmospheric pressure decreases, right? If atmospheric pressure decreases, your calibrated airspeed will also decrease. Calibrated airspeed will decrease because calibrated airspeed is nothing but dependent on pressure, dynamic pressure. So higher altitudes means lower and lower atmospheric pressures, lower and lower registration of dynamic pressure in the ASI instrument. So calibrated airspeed that is shown to you will also decrease in value. And TAS, you are climbing at constant TAS. If you deliberately increase the true airspeed of your aircraft, the calibrated airspeed will also increase and remain constant. But if you fly at a constant true airspeed, calibrated airspeed is bound to fall. Now what will happen to Mach number? Now Mach number is nothing but true airspeed divided by local speed of sound. Now local speed of sound is equal to 39.17 divided square root of temperature in Kelvin. So it is directly proportional to temperature, right? Now at 5000 feet, let's say our atmospheric temperature is warm. It is 30 degrees Celsius. At 10,000 feet, it's a bit cold. Atmospheric temperatures will decrease, right? Lapse rate. It's 20 degrees Celsius. So what will be the local speed of sound at 30 degrees Celsius? At 5000 feet, it will be, let's say, 39.17 square root of temperature in Kelvin. So 30 degrees Celsius is how many Kelvin? 30 plus 273, that is 303 Kelvin. So square root of 303 into 39.17, that is 682 knots local speed of sound. But that same local speed of sound at 10,000 feet will be equal to how much? 39.17 square root of 293 Kelvin. The square root of 293 Kelvin into 39.17 is 670 knots. Right? So local speed of sound has decreased. Now let's calculate the Mach number. The Mach number at 5000 feet will be how much? TAS. Let's say TAS is 200 knots. Local speed of sound at 5,000 feet is 682. So 200 as a fraction of 682 is 0.29. Now the same Mach number at 10,000 feet will be same task 200 knots divided by 670. So 200 divided by 670 is 0.298 or approximately 0.3. So your Mach number will increase a little bit. 0.29 has become 0.23. Correct? That is only and only because local speed of sound has decreased. But now let's check the second part. Mach meter will increase in a constant task line, but if static source becomes blocked, what will happen if the static source becomes blocked? So the answer to this question, the theory or the explanation will be the same as the explanation I gave here. When you go to higher and higher altitudes, what will happen? I gave the calculation. If your static port is blocked, that means outside static pressure won't have any way to come inside the ASI instrument. So the altitude at which your static port got blocked, the static pressure available at that altitude will remain trapped in the ASI instrument. And as you climb to higher altitude, new pressure won't have a way to enter the ASI instrument. So all the calculations will be dependent or will happen on the basis of the old static pressure which got trapped in the ASI instrument. So what will happen, like I said, to your Mach number, as you go to higher altitudes, static pressure should decrease. But since the static port is blocked at lower altitude, where static pressure was much more or is much more than static pressure at any of the higher altitudes, that static pressure will be increased comparatively in a higher value. And the forward speed of your aircraft as you go to higher altitudes at constant true airspeed climb, the forwards to dynamic pressure registered by your airspeed indicator will decrease. Calibrated airspeed will go on decreasing because we look at the calculation 1000 minus 700 is 300. Okay, if the static ports were working fine or perfectly, the calculation would be 1000 minus 500, which is 500, more than 300. Okay, so with static ports working fine, functioning properly, no blockages, proper right value of static pressure will get registered and the dynamic pressure will be much more at higher altitudes than at lower altitudes. But without that, dynamic pressure will lag or will be under reading. Okay, so the final answer to this question will be how will Mach meter respond in a constant task line if the static source becomes blocked? The Mach number will decrease. Mach number will show decreasing values. It will underread. Okay. Next. The basic properties of a gyroscope are rigidity and precision. Very important. Rigidity and precision. SPL based Viva question. At a low bank angle, that means you are turning your aircraft at a very low bank angle, 5 degrees, 10 degrees, right? So the measurement of rate of turn, how fast you are turning your aircraft, actually consists in measuring what? Angular velocity, yaw rate, pitch rate. So the correct answer is at low bank angles, you will be measuring the yaw rate of aircraft. Okay, next. An airborne instrument equipped with a gyro, 2 degrees of freedom, and horizontal spin axis. So you have two instruments with 2 degrees of freedom, artificial horizon and heading indicator. So that means we have two possibilities. Now check the next part. Horizontal spin axis. There is only one instrument out of these two which has a horizontal spin axis, which is DGI. So correct option is option Charlie. When in flight, the needle and ball indicator is on the left and the ball is on the right. So you are flying in the air in the atmosphere. The aircraft has turned left hand side. The ball in the inclinometer has gone to the right hand side. So aircraft left, ball right. So this indicates a skidding turn. That means when ball gets thrown outside of the turn, it is called skidding turn. You are making a left hand turn, but the ball has gone to the right hand side. So that is called skidding turn. So that means turning left with not enough bank, turning right with not enough bank, turning right with too much bank. So you're turning left. Pay attention to the direction in which this aeroplane has turned. Left hand side. So you're turning left. And why does skidding happen? Skidding happens because you are not turning your aircraft, you are not turning with sufficient sufficient bank angle. That means you are turning your aircraft with rudders only, not with ailerons. Okay, with sufficient bank angle. What is the solution? Ideal solution is step on the rudder. So if the ball goes to the right hand side, step on the right rudder. Bring the ball in the center, make a coordinated turn or increase bank angle. Increase bank angle. Now why has this ball increased? To the outside of the turn. Why has this ball gone to the outside of the turn? Because it has gone to the outside of the turn to the right hand side under the influence of centrifugal force. Centrifugal force. So as a solution, I gave you two solutions. Step on the right rudder or increase your left bank angle. Increase your bank angle of aircraft more to the left hand side because that's where you want to turn your aircraft. Okay, so if your current bank angle is 10 degree, that means it's not enough. Make it 15, make it 20 degree and see, check what happens to the ball. If it comes in the center, that means that is the right bank angle. Okay, so do that. Increase your bank angle. When you increase your bank angle, you are nothing but increasing the centripetal force of your aircraft. Centripetal force is the inward force towards the center of the circle. So this centripetal force will pull this ball out, which is outside of the turn towards the inside of the turn. So the ball will automatically move from right hand side to the center under the influence of centripetal force. Okay. So very important question, practical. How many degrees of freedom and spin axis of an attitude indicator? Like I said just now, 2 degrees of freedom and local earth vertical and vertical spin axis. So option alpha. Direct reading magnetic compass will be affected by soft iron effect on hard iron and hard iron. So option Charlie. So it gets affected by your hard iron, that means magnetic materials in your aircraft, the metallic surfaces. Soft iron, that means magnetic latitude or magnetic lines of force or magnetism in the earth. So that is soft iron. So both of them. A turn indicator has a horizontal spin axis, no. Vertical spin axis, no. 1 degree of freedom, yes. 2 degree freedom, no. A spin axis tied to the yawing plane of aircraft, yes. A gravity erecting unit, no. So 3 and 5 are the right options. So option Charlie. Okay. This concludes our lecture. I hope you have understood all the questions that I solved in this video lecture. I do accept that the questions related to constant calibrated airspeed climb, mock climb, task climb are a little bit tricky, but they are easy to understand. So I have explained the concept in the way you can understand it, why we are marking a certain option, the logic behind that, what's actually happening. So I hope I have succeeded in that effort in explaining those questions in simple way to you. If you have any questions or if you want to add anything to that, you can let me know in the comment box of this video lecture. I do also request you all to share this channel and this video lecture with your friends. Subscribe if you haven't yet and hit the like button if you have genuinely liked this video lecture. In my next lecture, I will solve the next 10 questions. So I hope to see you there. Best of luck.